Hi there, and welcome back to my Precalculus video series, where my goal is simple: to make Precalculus make sense. Whether you're here to get ahead, catch up, or finally understand what your textbook is trying to say, you are in the right place. In the last few lessons, we've explored the structure of real numbers, their subsets, and operations we perform on them. Today, we take a crucial step back to visualize how real numbers are arranged on a line, the fundamental building block for everything we graph, compare, and calculate in this course. By the end of this video, you will be able to 1. Understand how real numbers are represented on the number line. 2. Describe the origin, direction, and coordinates of points on the real number line. 3. Use inequalities to compare values on the real number line. And 4. Interpret how the position of numbers precisely relates to their numerical value. Thank you for being here. Now let's get started. Think about everyday tools like a thermometer, a ruler, or even tracking your bank account balance. They all rely on a continuous scale, a line, to represent real numbers and their relative magnitudes. What does it truly mean for a number to be to the left or right of 0? Why is -3 smaller than -2, even though the absolute value of 3 is larger than 2? Today we'll build the intuition that drives everything from basic arithmetic to the advanced concepts you'll discover later in calculus. The real number line, which is often just called the real line, is a straight line that extends infinitely in both directions, symbolizing that there's no end to real numbers, positive or negative. At the center of this line, we place a special point called the origin, and we assign it the value of 0. From the origin, we establish a unit length. This could be any consistent distance, like 1 centimeter, 1 square on graph paper, or 1 tick mark on a ruler. This unit length allows us to consistently mark out all other real numbers. Every point to the right of the origin represents a positive real number, and every point on the left represents a negative real number. So the number 4 is represented by a point precisely 4 units to the right of the origin, and the number -4 is precisely 4 units to the left of the origin. We call the location of each point its coordinate. When we place real numbers on this line using coordinates, we also build the essential foundation for the Cartesian coordinate plane, which we'll explore in another video. Now here's where the real number line becomes incredibly powerful. It provides a visual and conceptual framework for understanding order, for comparing any two real numbers. If you have two distinct real numbers, say A and B, their positions on the line tell us which is greater or lesser. We define the relationship as follows. A is less than B if and only if the point corresponding to B lies to the right of the point corresponding to A on the number line. Alternatively, and more formally, we can state that A is less than B if B minus A is a positive real number. This rigorous definition of less than applies universally to all real numbers, including integers, fractions, and even irrational numbers like the square root of 2 and pi. Let's draw out a few examples. Let's draw the number line that represents this inequality. -5 is less than -4.9. I'm going to draw a zoomed in version of our number line. -5 is this point right here. This could be our A. And -4.9 is right in between -4.8 and -5. This could be our B. If I do B minus A, where B is my -4.9, and I subtract my -5, this will result in -4.9 plus 5 because of those properties of subtraction that we talked about in a previous video. If you missed that video, you can find that right here. This will result in 0.1, which is a positive real number. That's how we know -5 is less than -4.9. So we could tell through the subtraction, but we also know because -4.9 is towards the right of letter A. Here's another. -pi is less than -3. Let's draw another number line. I'm going to start it at -2.9, -3, -3.1, -3.2. We know that pi is approximately 3.14. this is the coordinate of negative 3. And 3.14 is a little bit past the 3.1, but a little bit before the halfway point. So here would be my 3.14, and this my 3. So the coordinate that's to the left would be our A, the one towards the right would be our B, and that's what makes this inequality true. If I did B minus A, I would get negative 3 for B minus, I would get negative 3.14. This would turn into negative 3 plus 3.14, which would just be left over with my 0.14, which is a positive real number. That's how we know A is less than B, or in this case, negative pi is less than negative 3. This visual understanding of inequality is absolutely crucial in precalculus. It forms the basis for reading, writing, and interpreting mathematical statements such as A is less than B. What we read as A is less than B really means that A is strictly less than B. There is no other option. A will always be less than B. Another one is A is less than or equal to B. A third one is A is strictly greater than B. And lastly, A is greater than or equal to B. In precalculus, this fundamental concept will directly evolve into skills like solving complex inequalities, precisely defining the domains of functions, and even grasping the core ideas of limits and continuity once you're ready for calculus-based ideas. Let's test your understanding. Imagine you're standing at the origin of an imaginary number line, and someone gives you the instruction, walk 3 units in the direction of negative pi. What direction do you walk in? And what type of number do you expect to land on? Pause the video here to think about your answer. Well, if you receive the instruction, walk 3 units in the direction of negative pi, well, negative pi is a negative number. You would move to the left of the origin. And because you're moving left, you would end up at a negative real number, 1, 2, 3 units away. That number that you would land on, whatever unit of measurement that you're using, would be negative 3. This demonstrates that even irrational numbers like negative pi define a clear direction and have a precise, unique place on the real number line. To summarize our key takeaways from today's lesson, the real number line is an indispensable visual representation of all real numbers. Every point on the line corresponds to a unique coordinate. Direction matters. Movement to the right signifies positive values, and movement to the left signifies negative values. Inequalities precisely express the relative order and position of numbers on the line. In our next lesson, we'll expand on this by learning how to use interval notation and set builder notation to describe entire continuous sections of the real number line, not just isolated points. That's where things get really elegant and powerful for describing mathematical solutions. If you found this video helpful, please hit the like button and consider subscribing so that way you never miss a step in this comprehensive precalculus course. And if you're ready to practice what you've just learned and deepen your mastery, I've created a printable homework and quiz pack specifically for this lesson. You can grab it from my Gumroad store, linked directly below. It includes homework problems and a quiz with full solutions. Thank you for spending some time with me. I will see you in the next lesson.